Swayam Prabha. Digital India. Educated India.
Hello everyone. So we'll continue with the fiber fineness measurement. Our next technique is that fiber fineness by airflow method. So this is actually, it's a very quick method, and here this method is used for mill practice, and because of its speed of measurement. Here the principle is that when air flows through a surface or through fiber, depending on the surface area, the surface of fiber exerts a drag the airflow. So air flow rate changes with the surface area present. So this is happening for any fluid flows through the any solid surface. Now let us see example of say river or any stream flowing. So this is a stream flowing, stream of water flowing through a channel or a river. At the bank of river, the side river, the water is in touch with the solid, that is the sand or soil, where during the flow this surface will exert a drag force. So, and which will resist the flow of water. So at the edge it is observed that the speed of flow is slower than the central part. This principle is used here in airflow method. So airflow rate at a given pressure difference through uniformly distributed fiber mass is determined. So if the airflow is more for a particular mass of fiber, so here say for cotton fiber, we use typically airflow method for cotton and wool fiber, very commonly used. And the same said W mass of fiber, cotton fiber, is packed here. This is the coarse fiber, another W mass, fine fiber, cotton fibers are packed. And air is flown through this surface. And depending on the surface area, total surface area within this mass, W mass, so mass is constant, so depending on the surface area, the air drag will change. So which will result differential airflow. Now a coarse fiber results lower specific surface area. What is specific surface area? Total surface area per unit volume of fiber. So for a constant mass of fiber, that is actual volume of fiber, the airflow is inversely proportional to the square of specific surface area. So as the specific surface area increases, the airflow rate decreases. So for coarser fiber, the specific surface area is less. So airflow rate will be high. So effectively, for a particular fiber, say cotton, with a particular mass, we can gauge the machine, the equipment. So for a particular airflow rate, if we place a fiber with a known micronair value and the flow rate is recorded and it's gauged as certain micronair. So in airflow tester, the vertical tube column is actually gauged in terms of micronair scale, although we measure the airflow rate. So specific surface area, if we want to calculate, this is the total surface area pi d into L. So for a L length and total volume pi d square by 4 to L. So it becomes typically 4 by D. So it's inversely proportional to the diameter of fiber. So as the fiber diameter increases, so specific surface area decreases. So we can get the relationship between the airflow and the diameter if we combine these two equations, and ultimately what we get, the airflow rate is directly proportional to the square of the diameter and which is directly proportional to the mass per unit length or micronair. So here you can see in airflow tester, in place of airflow rate, we gauge it in terms of micronair. So let us see the animation. Now we can see here the fibers are packed in the chamber, fibers of known mass. Then we start the pump to take out the air through the fiber mass, and for a certain pressure drop we can measure the airflow rate. Okay, so this is the pressure drop. Certain pressure drop is there, delta P, and the airflow rate is measured, which is actually showing the micronear value. So in this way, we can directly and quickly measure the fiber fineness in micronear. So this is the schematic diagram where fibers are packed in the fiber chamber. In this fiber chamber, fibers are packed, and when the suction pump started, the airflow rate is measured and pressure gauge for certain pressure difference, we can measure the airflow rate. The principle can be reversed also. For certain airflow rate, we can also measure the pressure drop. That can also be the principle. In that case, we have to gauge the instrument in terms of pressure drop. Now with another animation, let us see what happens if we change the fiber micronear from coarser fiber to finer fiber. When we change, we will see if we change the fiber here from coarser to finer fiber, for constant air pressure, the air flow rate will reduce. Here you see that initially a normal fiber, it's a coarser fiber, is being packed, and then the instrument is started. Like earlier case, the float will rise up depending on the micronear of the fiber, fineness of fiber, and it is reaching at certain height. This is the micronear value of this particular fiber. Now what we will do, we will change the fiber, this fiber, replace this fiber with a finer fiber. So coarser fibers are being replaced by a finer fiber. Now we have placed finer fiber here, and we have got the micronear. So this difference in micronear, you can see it's depending on the air flow. So here if you see, M1 is the micronear of coarser fiber, which resulted the higher air flow rate, and micronear 2 M2 resulted the lower flow rate. So by measuring the air flow rate, we can calculate the space, we can measure indirectly the specific surface area, and using pre-calibrated fiber, so we can measure the fineness of the unknown fiber. Okay. So this relationship we have discussed. So it flow two types of measurement of airflow for a constant pressure drop, and measurement of pressure drop for a constant airflow. Now try to see what is happening here. when we are changing the coarser fiber with finer fiber. Now here two representation, one is this is for coarser fiber and equivalent finer fiber. And the thing is that we are taking the same mass for both the cases. As both the fibers are cotton fiber, their density of the fibers will be same, so total volume of fibers will be same. Now let us see the to have the total volume same. Okay, what will be the difference in the diameter of the fiber? So which we have observed here. So ratio of diameter of 1 and diameter 2 will be it's a 4.94 divided by 3. With that relationship, if we have this type of relationship, then we can achieve the total length of total volume of fiber, coarser fiber in L length and total volume of finer fiber in L length are exactly same. Okay. Here if we replace this ratio, finally what we get, the surface area of fibers in L length, and here the surface area of fiber in L. So here it is 7, here it's 11.54. So that means for same mass, the surface area presented will be higher for finer fiber, and that will actually affect the airflow rate. Okay. Now let us try to see if we make some mistake. So in the laboratory, we are trying to test the micronair. So in micronair testing, the following mistakes were made. First, if we take higher quantity than the specified, this is cotton fiber. Suppose in a standard, in the instrument it is written, you have to take say 4 gram of fiber, 4 gram fiber, and then we thoroughly open the fiber and then we put the fiber in the chamber. Another case, instead of taking 4 gram, we have taken higher quantity, say 6 gram we have taken, and again we have tested, we have opened it and we are trying to test the micronair. And second case, the proper sampling technique says you have to open it thoroughly you have to open, but in what mistake we have made, we have not opened it thoroughly, we have simply put it without opening. Now when we take higher quantity, that means what we have done, we have taken higher quantity fiber, means it will have higher specific, higher surface area. Higher surface area of fibers will be present, and this will result lower airflow. Lower airflow. So as we have seen, airflow rate, higher airflow rate means in a micronear testing, higher airflow rate will indicate the coarser fiber. And as by mistake we have placed higher quantity, so lower airflow will result, and it will show as if it's a lower micronear. That means it will show finer fiber, which is not correct. That means, for example, suppose a 4 micronear cotton is there, the reading should be, airflow should be showing 4 micronear, okay, microgram per inch. But when we have placed, in place of 4 gram, we have placed a 6 gram. So that means airflow rate will be, the float will rise little bit lower height. So it's say showing it is going up to this height. So it is showing 3 microgram per inch. That means when we take higher quantity by mistake, we will have wrong result, which will show the fibers are as if fibers are fine. Similarly, when suppose we have not opened the fiber properly, fibers are not opened properly, that means all the surfaces of the individual fibers are not been taken into consideration. So this is the lump, fiber lumps are there. So fibers, air will try to pass through this opening, so which will result lower surface area. And effectively the airflow rate will be higher in that case, and which will result as if it's a coarser fiber. So due to this, all this type of mistakes, we can get wrong results. Now let us try to solve few numericals. To calculate the change in airflow percentage change when the cotton fiber of 4 micronear is packed in a chamber of airflow instrument in place of 30 micron wool. Considering the surface characteristics are same, so 30 micron wool was there. So in an instrument, so 30 micron wool was there. Now we are placing 4 microgram per inch cotton. Specific gravity are given. Now we have already seen that the airflow rate is proportional to the square of diameter. So first let us calculate the diameter of all these fibers. So cotton micronail is 4 microgram per inch, and from that directly we can get the denier of fiber. The relationship of microgram per inch to denier is 2.82, so 1.42 denier. Specific gravity of cotton is 1.52 given, so diameter of cotton we can calculate. This is the considering the fibers are circular. Also from specific gravity of wool we can calculate the mass per unit length also. So here micronair is given, so diameter of wool is 0.03 millimeter. So we can get the percentage change. So airflow is proportional to diameter square. So change in airflow rate. So from wool to cotton, this will be the percentage change. We have got the diameter already. So from there the percentage change will be 86.18%. Next numerical will be similar. Percentage of 4 micronair of cotton is replaced with 1.2 denier polyester. So initially 4 micronair cotton was there. Now we are replacing with the 1.4 denier polyester of same mass. Okay. Assuming the total volume of fiber in both the cases are same. The total volume here we are talking about the total volume of fiber. So specific gravity of polyester and cotton are given. So again we have to calculate the diameter of fiber. So diameter of 1.2 denier polyester is can calculate 0.0111. Then specific surface area, we know it's a 4 by D. So specific surface area polyester we can calculate. This is the specific surface area of polyester, and denier of cotton using the standard formula, conversion formula. So 1.42, and diameter of cotton from that, this is the diameter of cotton 0.0115. This we have calculated earlier also. So specific surface area is, so we can use either specific surface area or diameter. So airflow rate is proportional to reciprocal of square of specific surface area. So using the same relationship we can get the percentage change in airflow rate. So alternatively by using diameter also we can get the same result. Okay. Next numerical is calculate the percentage change in airflow rate if the same mass of 1.2 denier polyester is packed in a chamber when airflow instrument in place of 20 micron. Okay. Assume that the total volume of fibers in both the cases are same. So basically it will be same volume, you can say, because the volume are same. The fibers are considering the fibers are circular in cross section. The calculation will be in the same way. So micron 20 micron wool. So diameter is given. Polyester denier we can convert it to diameter, and from there we can calculate the percentage change in airflow as we have done earlier. So square of diameter of wool minus square of diameter of polyester by square of diameter of wool expressed in percent. Next, similar numerical. Here both the cases we have wool. So one is 60 micron wool and packed in a chamber of an airflow instrument, volume 16 cubic centimeter, and in place of 20 micron. So here 16 cubic centimeter, in the relationship the volume of the chamber doesn't come, only we need the diameter of wool fiber. So just see, in place of 20 we are using 30. So 30 minus 20 by 20. So effectively 125%. That means when we are using a coarser fiber, so the airflow rate will be increasing. Next technique is the optical fiber diameter analysis. So this is basically its automated version of the microscopic technique we have discussed earlier. After making the preparing the slide, we place it to microscope platform, and then the data, the pictures are captured automatically, and the platform moves in zigzag fashion, and we can grab the data. Microscope stages move with the help of two computer controlled stepper motor, so that in zigzag fashion it moves. Through image analysis we can get the diameter data. And light scattering technique is there, which is known as fiber diameter analyzer. Here fiber thickness is measured at very fast, and this is used for synthetic fiber also. So it's a non-microscopic technique. Okay, works in light scattering principle. Initially fibers are cut in a very small pieces. Very small pieces of fibers are cut, and then it's suspended in a solution. Normally it's used isopropanol is used, because the fibers don't get swell and there is no reaction with the fiber. One can use other fluid also. So first to form a slurry of fiber. So fiber slurry is there, so liquid, and this fibers, this mixture is passed through a chamber, okay, through a tube, and which intersect with a circular beam of light, and which is projected at right angle. So if there is a this is a flow of liquid, fibers are flowing in this direction, the light will be at right angle. Light beam will fall on right angle with very thin light beam, 200 micron dia, and which will actually, that intensity of scattered light will be proportional to the projected area. So light will get scattered. Now this is the principle here. Now if we see here the fluid along with the fiber are flowing through this, and light beam is projected at right angle. This is a top view. If you see the side view, the light beam is created, and through a pinhole light is projected on a beam splitter. This beam splitter's function is that it splits the light into two equal parts. The right angle which is falling here with the reference detector, it measures the intensity which is a reference intensity, and when there is no fiber, no obstruction is there, in that case the light will fall to another detector here with the intensity I. So when there is no fiber, the same intensity will be there, so that will show that there is no fiber present. In case of the fiber, any fiber present here, this fiber will give some obstruction, and which will result the intensity, effective intensity I dash, and which will be lower than I. So this difference between I and I dash is proportional to the diameter of fiber. So in this fashion we can measure the fiber diameter at very faster rate. Okay. And flow rate and concentration of slurry are such that fibers are intersected with the beam one at a time. So it intersects that beam once at a time. Now let us see the animation here. Now liquid is flowing. Normal liquid is flowing with the fiber. Okay. Now the light beam is projected. Typical laser beam is projected here, and it is getting splitted into two parts, equal parts. Two equal parts. Now we can see, as the fiber presence is there, the fibers which is reaching the light intensity of light which is reaching to the other detector is less, and where the intensity is I2. Initially on the reference detector it was I, so and if the fibers are there, so it will be total detected, the light will be I2, as I have already explained. And the split detector is used just to ensure that we are taking the fiber diameter, correct fiber diameter. The fibers which are not passing through completely the beam, suppose this is a beam and a fiber is passing through us at the edge of the beam, that has to be eliminated. The reading has to be eliminated, which is done through the split detector. So this is capable of measuring at very high speed, so 50 fibers per second. So we can get a large number of data quickly. Next technique is vibration technique. And vibration technique, we know that here it's used for measuring the fineness for individual fiber, one fiber at a time, using the theory of vibrating string. Okay, vibrating string theory we can use. We can measure the mass per unit length of fiber. Now here one string which is connected with a jaw and other part on a through a point, knife edge point, and weight is hanging. W weight is hanging, so that a certain tension is applied, which is equal to Wg. This mass is there. If suppose if it is say weight, so this is the equal to tension. Okay. So we know the basic theory, the relationship between the natural frequency, tension and fineness of any string, the mass per unit length of any string. These are related as F is the frequency, natural frequency, that is resonance frequency, but 1 by 2L, L is the length of the string, T is the tension applied on the string, and M is the mass per unit length. Here tension, here that is weight which is hanging, that is the tension applied on the string. From there, by rearranging, we can calculate the linear density or fineness of fiber, where F is the fundamental natural frequency of vibration in hertz or cycle per second. Tension is given in dyne, mass per unit length, gram per centimeter in this unit, and free length in centimeter, which is actually half of the wavelength. This, if we say it's wavelength, and this is the half of the wavelength. This is the wavelength. So string is clamped at one end and laid over a knife edge support loaded by W weight, and then the vibration is introduced here through the transducer. We are introducing the vibration on the string. Here in present case it's a fiber, and we change the frequency so that we can calculate the resonance frequency for a certain tension. Length is known, so tension is, if it is mass, then it will be Wg, and initial tension we have to keep with a certain limit, and we simply in mass gram per centimeter, if we can convert it to that formula using the denier. So in this relationship, the mass per unit length gram per centimeter can be converted to the denier directly. Denier we can get, because mass was the gram per centimeter. So if we multiply by 9 multiplied by 10 to the power 5, we will get directly denier. So the fiber is then caused to vibrate either by vibrating string or by using transducers with a range of frequencies till we get the resonance frequency. So what is that? The frequency which gives the maximum vibrating frequency, it's a resonance frequency from which the linear density is measured. So we can have some correction factor if the same fiber with different Young's modulus is there. So using this correction formula, we can get the actual fiber linear density. Now let us try to solve some numerical. In a vibroscope is a commercial machine which uses the vibration principle. In vibroscope, the tension applied on the fiber is 150 dyne. So T is 150 dynes. And free distance, the L is 20 millimeter. Natural fundamental frequency of vibration is 1.5. F is 1.5 kilohertz. So we have to calculate the denier of the. So using directly that formula we can calculate. Okay, that we have used 22. So dyne was the unit of tension, centimeter was the unit of free distance, and hertz was unit of the. So 1500 will be 1500 hertz. So fineness we can calculate using the given relationship. This relation directly we can use that Wg is the tension, 150 dyne, and this was the relation, it's a 2L, so 4 centimeter, From there we can calculate the denier, 3.75 denier. Okay. In the instrument we get directly the value because our this load is known, length is fixed, so that we can directly get the value. Now 1 kilometer of wool fiber weighs 0.48 gram. What will be the gravimetric diameter of wool in micronair? So we can see it's not the related with the vibration method. So we can use first, let us use this part. So what we will do, we will use using this data, we will calculate the mass per unit length. And first gravimetric diameter of wool we should calculate. So wool fiber fineness in denier is, so 1 kilometer weighs 0.48 grams, so 4.32 will be the 4.48 multiplied by 9, so 4.32 is the denier of fiber, wool fiber. And this wool gravimetric diameter that we have already calculated earlier using the standard formula. Now wool fineness is known, tension applied is 200 dyne, free distance and support is asked for, which is x. Let us assume x. Natural fundamental frequency is 1000 hertz. Okay. And using the standard formula, so the diameter of wool in micron, using the standard formula we are getting 21.59 micron. This is the micron of wool. So vibroscope relationship. So this is the standard relationship we have discussed, and where tension is 200 dyne, this is 2 multiplied by x, wavelength. So from there 4.32 was the denier of wool, and just replacing, this is 4x square because lambda square, so 4 square, and this is the frequency 1000. So by solving this we get the length value as 3.227 centimeter. So that's the basically actually free distance between the clamp and the support. Next is that a 3.5 micronair cotton fiber is tested in a vibroscope with a free distance between clamp and the support being 2 centimeter. So L is 2 centimeter. What will be the applied tension? T is asked for in dyne to have a natural fundamental frequency of 2.5 K. So frequency is 2500 Hertz. Okay. L is given. So first thing is that we have to calculate the denier of this fiber. So denier relationship, tension is no, free distance is given. Denier and microneer relationship one can derive. So this is microneer divided by 2.82. We can directly get denier 1.24 denier. So it's a microgram per inch, and denier we know that gram per 9,000 meters. So if we convert, we get this factor 2.82 factor. So fiber fineness in denier. So using the earlier relationship, we can get so the T value. So T is unknown here, but rest other things are known. So the wavelength is 4 centimeter, and we get the T value 137.78 dyne. Another numerical similar in a vibroscope. So tension is applied 150 dyne, and the free distance between the clamp and the support is 2 centimeters. L is 2 centimeters. L is 2 centimeter. So frequency is 1 kilohertz. Tension applied on the fiber sample is given. Free distance is given. Frequency is given. So decitex we have to calculate. So first we have to calculate the denier as per the standard formula given. So denier is 8.43 denier, and from this denier value we just the decitex is 10 by 9. So this is the decitex of the fiber. Denier equal to decitex, 9.37 decitex. Another numerical, so mass of 18 kilometer polyester filament is 7 gram. The above polyester filament is tested on a vibroscope with 200 dynes tension applied on the specimen. What will be the resonance frequency? Here frequency is asked in kilohertz, frequency of vibration if free distance between the clamp and the support is 3 centimeter. So consider the specific gravity of polyester is this. So first what we have to do, we know the length of the polyester filament and mass is, so we can calculate the denier of polyester filament. Okay, so all the data are given. So fiber fineness is 7. So from there we can calculate the denier from length and mass. Then by using the standard relationship, we can calculate the frequency. So this is the denier which is calculated, tension, and here this is the wavelength square, frequency which is required. Okay, and by solving this relationship we can get the frequency of 1.19 kilohertz. This is the frequency. Now let us see another problem here. So during the measurement of fiber fineness by vibration method, the following mistakes were made. So we have seen in case of measurement by airflow, we can make some mistakes. Here let us see the mistakes are, what are the mistakes? Used higher tension in fiber specimen than specified. So this is the tension, we used higher tension. So if as this linear denier is directly proportional to the tension, so if we use higher tension, our result will be coarser. It will show higher that the fiber is coarser than the existing fiber, the normal. Another problem was the used higher free length of fiber specimen than the specified. That means wavelength, this is higher. So if we use this higher, we will get the result. It's a denominator. So here the denier will be less. So but one can see that here it's a square of the length. That means small change in length will affect the denier in a greater way. Okay, so we have completed the fiber fineness part, and in the next session we'll discuss the analytical approaches of measurement in fiber maturity. So till then, thank you.